My name is Johanna Wagstaffe. I'm a meteorologist and an earth scientist. Every day, I see the effects of climate change through my work, a relentless cycle of extreme weather, terrifying storms, deadly heat domes, wildfires, droughts. But I remain in awe of the natural world and how it finds ways to adapt. And that's what we explore on Planet Wonder. Polar vortex, atmospheric river, heat dome. We know these weather phenomena connected to the jet stream are changing. So that got me wondering, what's going on way up there that makes weather down here so extreme? Speaking of up there, talk to me, Goose. When you think of the jet stream, are you thinking of jets, planes, flying? You're not alone. As a pilot, I love flying. This is my dad and fellow pilot, and the one that got me interested in flying. When I was 12 years old, I joined the Air Cadets, and my dad took his first flying lesson. He was inspired by his great uncle and World War II pilot. These days, my dad and I fly together in his 1943 World War II tail dragger, an Aranca L-3B used by the U.S. Army for observation and liaison, to be exact. And yes, I have to reconcile my carbon footprint with being a private pilot. Carbon credits do help. But it was actually getting my pilot's license as a teenager that I was first introduced to meteorology and eventually climate change. The jet stream is where planes catch a ride in what is essentially the highway in the sky. Okay, not this exact plane. This one does better closer to the ground. But it's that very view of the meandering rivers down below as we navigate the winds and the weather around us that has me thinking about the similarities between what's happening above our heads and below our feet. The same conveyor belt that helps give a boost to the big planes is what carries weather systems around the world. And it's that weather that is coming with greater frequency and intensity because of our warming climate. As a meteorologist, I want to know more about how these conveyor belts are changing. And as a pilot, well, requesting permission for a flyby. To learn more about these elusive rivers in the sky, we went from a bird's eye view to a fisheye view and met up with atmospheric scientist Rachel White in the Pitt River, literally in the river. Right where the Pitt Lake empties into the river, a stunning backdrop for bird and weather watchers alike. So we're standing in the Pitt River. How does the jet stream behave like the river?
That's a great analogy for what's going on with the jet stream. And so if we think about rivers, we've got this flow of water going in one direction. And, we can think about the storms that the jet stream are bringing along, like some of the eddies that we might see in the river. You see that they get advected, they get taken along by the flow of the river. And also, if you think about rivers, you think they do meander. You see these loops. They're on a different time scale to what's happening in the jet stream. And so the jet stream is creating these meanders and these loops, and they're changing on a time scale of sort of days to weeks.
Rather than millennia.
Exactly, which is what's happening with the river. But it's sort of that same thing of, you have pieces of river joining other bits of river. When we look up in the jet stream, it's not actually at any one point just one smooth jet. You've got all of these little bits of the jet stream, they curve around. And the jet stream is a lot wider than this river is here. And so up in the atmosphere, the jet stream is hundreds of kilometers wide. But, some of the aspects are very similar.
Do people know this? What can you tell me about the jet stream?
The jet stream?
Of the wind and the sea, like the currents and stuff like that. But I don't know much, and of course the sun, if it's summertime or winter time, that's all I know.
It's constantly moving, and if you really look at the weather and how nature is, you can pretty much see, kind of gives you a little message about what's coming up.
I mean, I know the oceans move because of the moon, right? I don't know if maybe it's the same thing or something close to it.
The Earth has not one, not two, but 4 primary jet streams that circle the globe, 2 around the polar regions and 2 around the mid-latitude regions. And that's because The Earth isn't heated evenly. The sun's most direct rays hits the equator, and we get the greatest temperature differences where those primary jet streams form. They can travel between 175 and 400 kilometers per hour, so that's why commercial jets often hitch a ride traveling west to east. Mwahaha. Okay, Rachel, what's going on way up there that makes weather so extreme down here?
Yeah, that's a great question. And whereas when we think about weather extremes, we obviously think about what's happening at the surface because that's what's impacting us. But when scientists and forecasters are sort of looking at this, they're usually actually looking at what's happening up in the atmosphere. And when I say up in the atmosphere, it could be as far as sort of 9 kilometers above the surface.
Okay, hold that thought. Experiment time. I want to demonstrate to you the two forces that affect the jet stream, the spin of the Earth and the temperature difference around our planet, and show you how that can drive atmospheric rivers. Using household items, namely a turntable. Make sure you ask your parents before you pour water on their turntable. Always wanted to say that. And various Tupperware. So this big glass bowl is a proxy for our rotating planet. The water in it is our atmosphere, and this jar of ice is the pole. So you're kind of looking down on Earth from the North Pole. We're gonna get this puppy spinning, low RPM there. And I'm gonna give it a few minutes so that the water spins uniformly unperturbed. Try not to play any music while we're doing this. It'll just be scratches. Okay, first we're gonna add blue food coloring close to the pole as a proxy for the polar jet stream. Let's see here, just a couple dabs. Now watch as the Earth rotates, those ribbons of cold air start to extend down towards the equator. And because of the Coriolis effect, which is the deflection of air to the right because of the spin of the Earth, we start to get eddies. And those eddies are actually what our winter storms look like across Canada. Ooh, this is looking good. This is a turbulent planet Earth right now. I love it. I count like 4 storms. Okay, now we're going to add green food coloring close to the equator, so the edge of the glass. And this is a proxy for our warm air. There we go, a couple drops here. We'll let that start to spin. And what you'll notice is the green, warmer air starts to fill in the gaps between the cold air. You'll start to see those ribbons stretch up from the equator towards the pole. And what this is doing in reality is transporting huge amounts of warm, moist air from the equator poleward. In fact, this is how the west coast of the US and Canada gets most of its water vapor via these huge atmospheric rivers. And that's really what you're looking at. These ribbons are atmospheric rivers that stretch hundreds of kilometers. Now, this is a very stormy planet Earth right now, but this is actually an excellent proxy for what's happening right above our heads.
And so what's happening up there is really sort of creating the systems. That's where systems are growing and developing that are going to affect the weather down at the surface. And there's different ways that extremes can happen, and all of them are affected by what the atmosphere is doing really way up. And so, for example, for heat extremes, and so if we're thinking about a heat wave that happens over the summer, usually what's happening is that we have a high pressure system that's sitting sort of over a particular region and it's staying still. And so we call this a blocking high, and it's called blocking because it sort of blocks any other weather systems that might be coming in, and they get diverted around this high pressure system, and then this high pressure just stays over us. And so for cold extremes, actually it's often a lot more to do with the meanders in the jet stream up above us that end up bringing in a lot of cold air from the north, essentially. And so when we have a meander where we have winds coming from the north towards us in the northern hemisphere, this is going to create pretty cold weather here.
As a meteorologist, I often think of the jet stream as the conveyor belt. for weather, and we look for blocking patterns like the Omega block here in North America. So they really are tied together.
Yes, they really are. And exactly that. The jet stream is sort of transporting a lot of our weather systems.
Okay, hold that thought. It's not only weather and planes that jet streams transport around the world. They'll take any kind of hitchhiker, including smoke and ash. By now, most Canadians have probably been affected in some way by wildfires on the other side of the country. Wildfires in Western Canada and California can get so intense and so large that smoke and particles billow all the way up into the jet stream. From there, they cross the 5,000 kilometers to the east side of the country. Then, when a weather system brings sinking air, it pulls the wildfire particles and chemicals down to ground level, sometimes bringing dangerously poor air quality. It also is often the reason for those eerily red and orange sunsets. That's because the smoke particles allow sunlight's longer wavelength colors, red and orange, to get through while blocking the shorter wavelengths of yellow, blue, and green. So it would make sense that volcanic ash is just as transportable. One of the most recent examples is the major volcano that erupted on the Russian peninsula of Kamchatka, sending ash 10 kilometers straight up into the sky and right into the path of the jet stream. A few days later, that drifting ash prompted flight cancellations across BC and Alaska. Oh, jet stream, you gotta start vetting your passengers. What about the disappearing ice? And the jet stream. What's this for real? So what do we know about how climate change is impacting the jet stream?
Okay, so there are some things that we know very clearly, and there is also a lot of uncertainty around this question. And the reason mostly why there's a lot of uncertainty is there's a lot of sort of competing factors. So one of the things that affects the strength of the jet stream, the main thing that affects the strength of the jet stream, is the change in temperature as you go towards the poles. And so it's warmer towards the equator, it's colder towards the poles, so we have this temperature gradient. And it's that temperature gradient that actually controls the strength of the jet stream when we're talking about this sort of mid-latitude, the jet that affects us here. And with climate change, we know that we have what's called polar amplification, and particularly Arctic amplification.
Stop for just a second. Arctic amplification. Let me explain. The Arctic is warming much faster than the rest of the planet, 4 times as fast, in fact, and Arctic amplification is the reason for it. As the planet warms, sea ice melts, exposing the darker ocean beneath it. Like wearing a black t-shirt on a hot day, the darker surfaces absorb more energy from the sun, causing more heating, and you guessed it, in turn, more melting, so on and so on. That whole process is what we call a feedback loop, and it's the main driver behind sea ice and permafrost melt, sea level rise, and changes to the jet stream. So let's go back to what we know powers the jet stream, and that's a big temperature difference between the poles and the tropics. And if the Arctic is warming and getting closer in temperature to the tropics, that temperature difference is getting smaller and the jet stream is getting weaker. In theory, the weaker the jet stream, the more likely it is to loop and meander rather than flowing straight and fast from west to east. In theory, that would lead to more extreme weather. But that's just one piece of the puzzle.
But that bit of the puzzle isn't completely clear. And so there's 2 things that make that more complex. The first thing is this thing with the Arctic amplification is what's happening at the surface. But as we just said, the jet stream is really happening way up high in the atmosphere, sort of 9 kilometers above where we are now. And if we look there, actually, we have potentially more warming in the tropics than we have up in the poles. And so now we're actually strengthening that temperature gradient.
Interesting. So we know that the Arctic is warming faster at the surface.
Yes.
We don't necessarily know that it's warming faster up high.
Correct. And so we've sort of got this tug of war of what's happening at the surface and what's happening higher up in the atmosphere. And so that makes it kind of harder to know exactly sort of where is the jet slowing, where is it speeding up, and how is that going to impact these meanders, these loops, a big weather system that cause these weather extremes. We do know some of the reasons for the Arctic amplification really is what's happening in the Arctic, but this connection between the two, it's not 100% clear which direction it's going. And some research says it's going from the Arctic to the mid-latitudes. Some research says it's going from the mid-latitudes to the Arctic. My perspective is it's probably a bit of both, and both these things are happening, and that's what makes it a really hard question to really tease out exactly what these impacts are.
And also an exciting area of research.
Exactly.
Whatever is changing the jet stream, where you feel it is in an airplane. This is your cabin crew speaking. We're experiencing some moderate turbulence. Please return to your seats and fasten your seatbelts forever. Okay, maybe not forever. But heads up, climate change could make air travel a whole lot bumpier. In fact, according to the study, by the middle of the century, the volume of airspace experiencing light turbulence could increase by about 60% and severe turbulence by almost 150%. Clear air turbulence, the kind that happens without the presence of clouds, is the result of wind shear, which is a change in wind speed or direction over a short distance. That rapid change in airflow is what can lead to bumpy conditions. And the jet stream contains about 3 times more clear air turbulence than the rest of the atmosphere. It's also the jet stream where commercial airlines take advantage of that fast-moving air when traveling from west to east. It's at this height, between 9,000 to 12,000 meters, that some research has already begun to detect an increase in the wind shear. And that's because at these heights, the air above the tropics is warming faster than the air above the Arctic, resulting in an increase in temperature difference that drives the jet stream faster and as a result, drives more wind shear. The more CO2 concentrations in the atmosphere, the more this trend looks to continue and the more air turbulence the models predict. So what does this mean for the future of aviation? Well, there's hope that the skill of clear air turbulence forecasts and in-flight detection will continue to improve. But at the end of the day, curbing CO2 is still the only real clear answer. Rachel, the jet stream, though, is still key for these extreme weather events that we are feeling more, like the atmospheric rivers and the heat domes.
Yes, it is still key. And so thinking about how these extreme events are changing with climate change, the way I think about it is there's 2 kind of separate pieces to this puzzle. The first one is, within science, we call this thermodynamic. And so it's really directly connected to the temperature changes that we're experiencing with anthropogenic human-caused global warming. And so, for example, with temperature extremes, this means we're going to see more and more intense heat waves. We're actually going to see fewer and less intense cold snaps. And we can also connect this to precipitation extremes. And so as we warm the atmosphere, we evaporate more moisture from the oceans, we've got a warmer ocean, and so then we have more moisture within the atmosphere. And so when we have these rainfall extremes, they can be more intense and dump more rainfall on us at a time.
And this is different than the dynamic changes, the big picture.
So the thermodynamics, that's pretty certain. Like how much change we get depends on how much we warm the planet. But we have this separate piece with the dynamics. And so this is connected to, is the jet stream changing with climate change? And how is it changing? And so if it is becoming more wavy, that means we could have even more heat extremes, but also potentially more cold extremes. And so that's why that's sort of a really interesting part of, by warming the planet, we could end up seeing more of these cold extremes. But we don't know that for sure. It goes back to this uncertainty about what's actually happening up there in response to these different pieces of climate change. And so that's what we're really trying to sort of get more of a handle on is, right, how is the jet stream going to change? How is the waves on the jet stream going to change in a warming world?
It reminds me about what we know when it comes to hurricanes and climate change. We know that the impacts of hurricanes are going to get worse, they're intensifying faster, but there's not necessarily going to be more of them.
That's exactly right. It's exactly the same type of argument.
That intensity was on full display in September 2022 when Hurricane Fiona battered Atlantic Canada, likely the strongest storm in Canadian history and one of the costliest weather events we've ever seen in this country.
Hurricane warnings, eastern Nova Scotia, as well as Prince Edward Island, Cape Breton, and southwestern Newfoundland.
When we talk about the jet stream, we know that the stronger the jet stream is, that means there's a stronger temperature gradient occurring between the higher latitudes and the tropics, which was certainly the case with Fiona. So what happened once Fiona moved northward and began to interact with that temperature gradient and the jet stream associated with it, we got that very vigorous transformation. If we look back into the hurricane records, these storms like Igor, Fiona, Dorian as well, storms that are hurricanes and then become very potent, the jet stream will often develop a large loop in it, and you will get almost a storm may completely stall in some of those situations. That wasn't quite the case with Fiona, but the way the jet stream interacted with Hurricane Fiona, it sort of drew the hurricane very rapidly northward initially, and then the forward motion of Fiona slowed down considerably. So if we see more undulations in the jet stream like this due to those, just the Earth's temperature patterns changing, we could start to see storms maybe more like Sandy or Fiona that tend to execute these, less typical paths because the jet stream is, making more of these larger departures in its path.
So the research continues. Are you hopeful that we'll find the answers we need fast enough to take action?
For me, it's important that we don't think that we need to have the answer before we do anything. We already know from this thermodynamic piece that extreme weather is going to become more extreme and more frequent because of climate change. This to me tells us all we need to know, that we do need to be doing something to reduce the amount of warming that we see. There's a lot of research still going on to really try to understand more about these extremes, and also to try and understand, can we use information about the jet to get better predictions of these extreme events? And so if we could have predictions on subseasonal, so a few weeks out, or even seasonal timescales of, is this season more or less likely than average to have extremes? I think that could be really useful information to help us adapt to the impacts and reduce the impact of these extremes on humans. But I do remain hopeful that if we really go for it, we can really mitigate some of the worst impacts that we're seeing in our climate models.
Scientists are using weather models to look for trends. Artists, like Bettina Matskun, use those same models for inspiration.
I like the weather maps, but also having a basic understanding of what's happening when I see clouds forming. I like to know their names. I like how meteorologists trace barometric readings with isobars, joining the dots. They talk about steepness, ridges, and troughs. I like to think about the atmosphere as a kind of invisible landscape moving above us. And now with satellite feeds, which I look at daily, it's fascinating and beautiful to see those systems gathering and changing. And I've been drawing these with a digital tablet, printing the drawings onto fabric and then embroidering them with small life forms. It's a way to gather the macro and micro together. I made a large textile funnel shape that goes from the jet stream at the top with symbols that indicate high winds down to the weather that's at ground level. I used old Gore-Tex and hiking boot laces as well as embroidery thread. I used sheer fabric and embroidery for the jet stream in the funnel piece and paint and just simple stitches in the butterfly that traces global jet stream patterns.
Ultimately, the jury is in when it comes to the fact that we will see more extreme weather in the future. But scientists are honing in on the intricate processes behind that. To quote Sir Elton John from his single Slow River, who is obviously referencing jet streams, the weatherman looks confused, shakes his fists at the sky.
turn this thing on?
I have to do it by hand. I have to go and pull the propeller down really fast.
This one.
This one is for the magnetos. So it's
What
got two
about this
magnetos.
one?
This one's the primer that you've got to put a bit of fuel into the
What
carburetor.
about this one?
That one there is for the carburetor heat. And this one here, that's for the cabin heat. That turns on the heat in the cabin. This is the stick you fly with.